Okay, YouTubers, today I'm going to show you how it's actually feasible to get energy out of water. A lot of people try to do this whole water car thing, and there's no way to get energy um, from nothing. You can't take hydrogen, you can't take H2O apart, separate it into hydrogen gas and oxygen gas, combine the same hydrogen with the same oxygen, and expect to get more energy. It just doesn't happen. There's no free lunch. However, if you go ahead and you take off, you have a H2O molecule here. If you go ahead and you take off only one hydrogen, so that you have an OH negative group, and you end up with another H, and you combine that with another hydrogen that you've done the same thing, you get H2, you get hydrogen gas. Well, it takes it takes a certain amount of energy to take off both hydrogens, which is regular electrolysis. It requires less than half of that to take off only one. And so you end up with a net energy. Well, the enthalpy, this all has to do with enthalpy. The enthalpy of this OH here is such that when you balance it all out, you don't get energy from nothing, because this OH goes off and it creates a endothermic reaction, combining with some sort of metal or salt or carbon in the environment. So that's how this works, and I'm going to show you all the equations. It all has to be done with enthalpies of formation. We'll talk about the enthalpies of formation. So enthalpies of formation, that is the energy that is put into or out of the system. If the sign is negative, it means that these molecules have this much energy taken out of them from the resting state. The resting state is defined as the molecule in its natural form. So H2, enthalpy of H2 gas is defined as 0, and the enthalpy of O2 gas is defined as 0. When you burn H2 gas with O2 gas, 285.8 kilojoules per mole of H2O come out of the H2 and the O2 gas. So the enthalpy of formation of H2O is minus 285.8 kilojoules per mole. Enthalpy of formation of H2, like I said, was 0, and O2, like I said, gaseous, was 0 as well. The enthalpy of formation of the hydroxide ion in an aqueous solution is minus 230 kilojoules per mole. So it's a little bit less than the formation of H2O. And these are just the values of gasoline when you combust it, and the mass of water, just some things that we'll be needing later. So we're going to start with the electrolysis equation. This is a partial electrolysis equation. It's not the complete equation. The method for a partial electrolysis is still to be decided. Most electrolysis actually takes off both hydrogens, and you're left with hydrogen gas and oxygen gas. I do not know how to remove one at a time, but it's much more efficient. If someone can come up with that, then they can use water for fuel. So we're going to take two water molecules, 2H2O in the liquid form, plus some energy, is going to end up with 2 hydroxide ions in aqueous form, plus 1 molecule of hydrogen gas. If we plug in the enthalpies of formation, we get 2 times minus 285.8 kilojoules per mole, and that is going to turn into 2 times minus 230 kilojoules per mole, the enthalpy of formation for hydroxide, plus 0, which is the enthalpy of formation for hydrogen. When we work it all out, we end up with 111.6 kilojoules per mole that comes out of every mole of H2O. Or actually, a correction here, that's per mole of H2, so per mole of hydrogen gas. 116.6 kilojoules are required to make 1 mole of hydrogen gas. This is if the partial electrolysis using this hydroxide ion is at 100% efficiency. Some experiments show that it's much more efficient than regular electrolysis, but I don't know if we can do this at 100% efficiency. But this is all theoretical. Maybe you could use some catalysts. Who knows what you might be able to come up with some chemical way of doing this equation that can give you very close to 100% efficiency. And if you do, then you end up using only 111.6 kilojoules to make